Hi, welcome back to Digital Logic Design. It's now time to add a hardware level to our top level design. So in this previous tutorial, we created this project, which I'm calling week 4 here because it's week 4 of the class that I'm teaching, right? Where we have this top level module, and we had a circuit where we instantiated the canonical SOP, the canonical POS. Right, so if I open the canonical SOP, in that previous tutorial, we wrote a Verilog module for this function f that has 3 inputs, A, B, and C. Right, the ones of the truth table occur in rows 0, 1, 5, and 6. And so we wrote a module right for the canonical sum of products, canonical product of sums, where we solve for the zeros. We had the minimized sum of products expression and the minimized product of sums expression. Right? And then we combined these into this top level Verilog file where we created an instance of each one of these modules. And we then took a look at that in the RTL viewer, which I thought I had up, but of course, here it is. All right. And this is what the top level looked like, right? Each one of those instances here is this symbolized as a block. We said we could go ahead and look inside those last time to see the actual gates that the bitwise operators implemented. Well, now that we have this top level, right, what we want to do then is create a hardware level where we can connect to the top level. And let's create a new module. And I'm going to do a new Verilog file. And we are going to call this is our hardware level module. And we're going to, what we want to do is we're going to connect A to switch 3. Actually, I'm going to say connect inputs to slider switches. And so A to switch 3, B to switch 2, C to switch 1, D to switch 0. And then we're going to show the state of inputs A, B, C, D, switches, right? The switches on red LEDs, 3, 2, 1, and 0. And so those LEDs are immediately above those switches on the development board. So you'll be able to see when your corresponding switch is in the 0 or 1 position. And then we're going to show the circuit outputs on red LEDs 9, 8, 7, and 6. So let's say we're going to, all right, and let's write a module. I'm just going to say something else, but we'll do that in the module. So module, I'll actually just call this hardware level. Right, and now we need to bring in the hardware signals. So input, and I'm just going to go ahead and address the whole bank of switches. Oh, sorry. No. Only switches 3 to 0. So input wire 3:3 down to 0, SW to match, right, what the user manual says for the DE1-SoC. We have to match those names. And then let's see, our output wire. And then here's where I'm going to address the whole bank of red LEDs. There's 10, 9 down to 0. LED R is the hardware name we need to use. End of our port list. And module. And so now if we wanted to connect signals A, B, C, and D to the switches in this module, we don't have any signals named A, B, C, and D, but we could create those as wires that are internal to the module. Right, so single bit wires, A, B, C, and D. And now I can say assign to A, well, assign SW3, assign to B, SW2, assign to C, SW1, assign to D, SW0. Right. And so we've connected the inputs to these slider switches. Right. What we want to do is we want to then instantiate that top level module. So here the top level module look like this. I'm going to copy the port list. Let's instantiate it with a name connection. Oh, sorry. There's only 3 signals, A, B, and C. There is no A, B, C, and D. I got carried away here. In your lab, typically, my students' labs, I typically work with 4 bits. In this example, though, we only have 3 bits of input. So we're going to use LEDs 2 down to 0. Okay, A, B, C. So 1, 0. Right. My most significant bit to my leftmost switch, so that as I look at the switches, it'll be easy to go ahead and associate the binary combinations so that the leftmost switch will correspond to the most significant bit of my input. The rightmost switch, switch 0, will be the least significant bit. I usually find that easiest when I'm working with the hardware. All right, so back to the instantiation. All right, so I want to connect to A in the top level module. Well, I could connect, I want to connect my A in this module. I want to connect to B, my B, and I want to connect to C, my C, and then to the various outputs. All right. The canonical SOP, let's just go ahead and make that LEDR 9. And each one of these outputs are 1 bit, so I can only connect, right, a single wire, single LED to that. So LEDR 8. All right, and I'm just kind of choosing these, I'm going to say at random to connect LEDR 7. But since all 4 outputs should be the same, I'd like to at least have them in the same bank, right? And dot min POS. We'll put that, keyboard is jumping around, sorry. LEDR 6, right? So when we have a bus, right, if we just use LEDR, that refers, the name alone refers to the entire bus that we've instantiated that's 10 bits wide. Because CSOP is a 1-bit signal, I can only connect 1 bit or 1 wire from that bus to that signal. So we have to use the bracket notation here, right, for the individual bit. Remember in the port list, when you specify the bus size, here in Verilog, you have to specify that out to the left. So we'd say 3 down to 0, bus size of 4, 9 down to 0, bus size of 10 for addressing all of the LEDs. And so now, right, these switch inputs should correspond to A, B, and C here. Alternatively, if I didn't want to create the A, B, and C in this module, alternatively, I could have just directly wired, sorry, switch 2, switch 1, and switch 0, and skipped that whole ABC thing. So it's whatever you prefer, right? As your students in my class or as you're learning this, go ahead and do what makes a little bit more sense for you when you read this. Right? All right, and the other thing I want to do is I want to show then the switch states on the LEDs. Show input switch states on LEDs. And so what I want to do is I want to assign to LEDR 2 down to 0. I want to assign switches 2 down. So 2 colon 2 down to 0. What this will do is this will show switch 2 on red LED 2, switch 1 on red LED 1, and switch 0 on red LED 0. Right? So I can address, right, this is a bus width that's 3 wide. This is a bus width of 3 wide. So the widths of your signals when you assign them need to be the same, right? Otherwise, you'll have some wire you're not connecting. And it will connect in order, the one on the left will be the most significant bit. So it will connect that one to that one and down to the least significant. So it will make those connections for you. Alternatively, you could have typed out individually, connect to LEDR2, connect, well, switch to, assign to LEDR1 equals switch 1 and LEDR0. If that makes sense to you, do that. Eventually, we're going to have to start getting used to working with the buses in this class as we get into large signals with more inputs and outputs. But if this one makes more sense to you, fine. You also could have done this. You could have just assigned A to that. Because switch 2, that input is connected to A, and this says, well, okay, take the value of expression A and assign it to the red LED. You could have done that as well, and then done LEDR 1 to B. Right. But you can't do all of these or you'll get an error saying you have multiple signals driving this. Actually, as a matter of fact, let's just go ahead and run analysis and synthesis and see that error. No, I need to save this. All right, and we're going to make that the top level. We'll just run analysis and synthesis on it. We should see an error about multiple signals driving the same output. Oh, we may not see it since they're all the same, but you wouldn't want all 3 of these in your design. It doesn't make sense. Oh, here's our error. Yeah, that's a syntax error. Parentheses, dot. Oop, I always miss out on that rightmost parenthesis there. All right. Well, it didn't come up with an error. And I don't think it came up with an error because these are basically all of the same signals that are driving this. Let's look at the RTL viewer. Tools, Netlist Viewer. See, I try to show you an error, but I don't generate one. Since they're all doing the same thing, it just got smarter and said, well, I'm going to connect these switches to A, B, and C, which we told it to do. And then notice that there's a wire coming over here, connecting it to red LEDs. So 2 down to 0 will connect it to red LEDs 2 down to 0. Now, there's a ground symbol in here. So see this wire coming down to here? This is a ground symbol. And it's grounded some things in our circuit. Now let's close the Netlist viewer. Like I said, I wouldn't do all of these. This is very confusing to read. So I'm going to get rid of that because I just want this now. Now, what we want to do is we want to pay attention to the warnings that we see, right? And so output port LEDR 5.3 at hardware level has no driver. Well, you've probably noticed, right? There are some LEDs in this bus that we said, well, we want this to be part of our circuitry, but we haven't said whether they should be on or off. And since they're in part of that bus where it says has no driver, there's no signal to say, well, again, should they be on or off? So sometimes when I use signals in a bus, and I'm not using all of them, I purposely either ground them or turn them on, but I'm going to say assign to LEDR 5:3, so 5 down to 3. And let's see, that's 3 bits, 5, 4, and 3. So 3-bit binary 0, 0, 0. And what I'm doing here is this 3 is saying the size in bits of whatever number I write to the right of this. So 3, and you have to have the apostrophe, it's part of the Verilog syntax. Next thing you write is the base. So B stands for binary. It says whatever I type to the right of this, interpret that as a binary number. And I just typed out the 3 binary zeros, right? I could have said, well, make the size of the signal 3 bits, but the base is hexadecimal. I could have just typed a 0. And what that will do is we'll turn that to a 3-bit binary 0, which is, 0, 0, 0. Or I could have said D for decimal. That's a decimal 0. What it would have done was it would have converted that to a binary 0, 0, 0. Typically with these circuits and these small bit patterns, I like to always type out the bit pattern there so I can see that. All right, and what that's going to do is that will still ground our LEDs, but it should get rid of this warning about it has no driver. I'm going to save that. Let's run analysis and synthesis. And we should see then a warning about it being grounded. All right. So now let's take a look at this warning. Output pins are stuck at VCC. So VCC would be a logic 1. GND is ground, logic 0. And LEDR, so 3, 4, and 5 are stuck at ground. Well, we did that on purpose. So we could look at those warnings as a designer right now and say, well, we did that on purpose. So that's not something that we're concerned about making our design not work correctly. And of course, as I'm writing up my lab report on this, when I've got these sort of warnings, I'd probably put these somewhere in an appendix in my lab report, and I'd refer to the, I'd write a section of my lab report about any warnings that are being generated. And I'd say, well, these 3 warnings are being generated. The reason is because I purposely said, right, to turn that bank of red LEDs off. So if I address that in my report, then that indicates that the rationale for these warnings that I have as a designer acknowledge the fact that they're there, and I'm taking responsibility for that behavior. Right now, I still have a problem here. Design contains one input pin that doesn't drive logic, and you're probably all yelling at me that when I changed my bank of switches, I didn't change that there to 2. So these warnings, right, are helpful, because that warning told me that I have an input, switch 3, it's not being used, so driving logic, well, it's not being used as an input to any of the circuits. All right, so I should save that, run analysis and synthesis. And I'm going to go up here to assignments, settings, and compilation process settings, use all available processors. Okay, I already had that one checked. I just don't want that warning about not using all processors. Save my work, run analysis and synthesis. And hopefully we'll take a look at any other warnings that are generated. Hopefully I won't have any except for the grounding one. Oh, and well, you probably yelled at me about this one now. See, not all warnings, not everything shows up at the same time. I might not have scrolled up enough. Verilog HDL instantiation warning at hardware level, line 25, instance has no name. So let's double click. And of course, I didn't give this an instance name. So instance 0, right? So I want to make sure that I address that, get rid of that warning. And my only other warning, and if I just want to go here to the warnings page here, right? This is the one we said that one's okay. Let's run analysis and synthesis. Again, to have gotten rid of the fact that I forgot to put an instance number there. Now, there are times when you generate warnings that your design, I'd say work with air quotes around it, but warnings you want to heed, because there will be times if you ignore warnings in your code, it will tell you sometimes when you have bad connections, when you haven't connected something. And if you don't pay attention to that and go ahead and investigate it and decide whether that's something you purposely put in your design and you can live with and record that, or right here, this is what we can live with, but if we had other things coming up, we would want to go correct that. All right, so we've got this hardware level design now. And what we'd like to do is we're going to start programming these to our FPGA board in class. And what we need to do is we need to make sure that we have the appropriate device settings. So I'm going to change here from files to hierarchy. And here, when I created this project, I just used the default device settings. So I'm going to double click here. And this is going to bring up this window for device settings. And now I want to specify a device. And the device setting for our Altera DE1-SoC board, it is in the Cyclone 5, Cyclone V family. It's in this family, so this is the correct set of hardware. By selecting this family, it's going to list here all of the devices in that family. Well, I can begin to filter that by typing 5 CSEMA 5F31C6, right? You could pick it out of the list. In this case, I happen to remember it. I type it in. That's when we want. We click on OK. Notice this changes here. All right. Now, what we also need to do before we program to the board is we need to bring in pin settings. If you go to Assignments and go to Pin Planner, right, what this shows you in the Pin Planner is we haven't imported any pin assignments. So what it always shows here is at the top are the names of the input and output pins in our top level design. So our top level design, we made hardware level. So here, and it shows these in alphabetical order. So switches down here, red LEDs here. And what we need to do is we need to fill in information about the location. And we can do that manually, but I want to take the easier route of importing pin assignments. I'm going to say Assignments, Import Assignments, and then you were given a link to in this assignment, in your lab assignment, right? My students were given the QSF file, and it's out there on Canvas. I've downloaded and put it on my desktop. So these 3 dots. Now these 3 dots open my folder that I'm working with, and there's always a QSF file within my folder, but this is not the one I want. This doesn't have pin settings, right? I've put this out on my desktop. It's called DE1-SoC.QSF. I'm going to say open. I say OK. And no error messages, right? In some versions of Quartus, it will come up and tell you it will put a message here saying it successfully imported the pin assignments. Other times you don't get that message, right? What we need to do now is that we've imported the pin assignments, right? We're going to go ahead and say compile design. We could just run analysis and synthesis, but if our pin settings are correct, our next step would be to actually program the board. So in order to program the board, we have to do more than just analysis and synthesis. We have to have this fitter. This has to run, I believe the assembler has to run it as well. We don't care about timing analysis, but we're just going to go ahead and say, double click on compile design. Compiling takes a little bit longer than analysis and synthesis, and let it run through the steps. Now, we shouldn't have any errors popping up unless we've made some error in the step of if we chose a processor that didn't match the pin settings we imported, that might pop up. We're going to have some new warnings popping up now, though, that we're not going to have to fix, but we will discuss briefly why some of these are there. Right. So we'll ignore this. Feature logic clock is only available with a valid subscription license. We're using the free one. No clocks defined in the design. Well, no, this is a combinational circuit. We don't care about the timing of any of this. It's not a clock driven circuit, so we can ignore that. We can ignore the synopsis design constraints file not found because that's required by the timing analyzer. All right. We get the same warning about pin stuck at ground, right? We can verify, yeah, that's the same one. We know that's fine. Now here's a new one, ignore location or region assignments to the following nodes. And if we open this up, right, we start getting this alphabetical listing of, right, about 580 or so different pins. That QSF file that we just used has pin assignments for every single pin on the board. So this one, I'm going to say, typically we don't need to open this, but I'm going to say open it, edit with Notepad. All right, sorry, opened it on the other screen. And this is what the file looks like, right? It has some settings, some information then that's telling, when we import this, that's telling Quartus how to deal with this. And so we're importing everything here. Now we could alter this. You could make a version. You could start getting rid of the ADC. You could start getting rid of some of these settings you're not using. You don't want to see that warning about it ignoring the pin assignments. For now, right, I'm comfortable with ignoring that warning and just taking the lazy route and importing all of these pin assignments. Another thing you can do is, right. Oh, so the other warning, some pins have incomplete IO assignments. Sometimes that has to do with voltage levels. It tells you you can go to the IO assignment warnings report for details. I think that it's usually under, right, under the fitter section, under the IO rules section. You could start reading through these. I've read through some of these before. These particular IO assignment warnings won't affect our design. There have been some of them that I've gone to the Altera website for the particular pins, and it's given advice about setting voltage levels or making changes. But even with some of those changes, it hasn't gotten rid of the warning. It hasn't stopped our class work from working. So this is going to be another one of those that we're going to say is safe for us to ignore, right, for our purposes. All right, so we've taken a look at those warnings. If we open up the pin planner again, so assignments, pin planner, you could have left it open from before, but notice now it's been filled in. Notice this area is filled in because we've imported all of the pins, right? If we look here, we still have at the top, right? These are the pins used in our top level design. That's what will always be at the top here. Out, you can see the direction. These are outputs, inputs here, right? And then it's got all the rest of these pins where it says the direction is unknown because we're not using them in our design. Right. But if you ever program your board and your board is not working as you expect and you've run a functional simulation and you know that your circuit is producing the outputs it should, it's usually a hardware issue. And it's often because you've something's gone wrong with importing the pin assignments. All right, I'm going to close this. Right. Something else you can do is if you want to get rid of some of those unused pin assignments, is there is an assignment editor. So assignments, assignment editor. And you can remove those if you want. So here where this says enable, I'm going to start with ADC, the analog to digital converter. If I just scroll down until I get to the first thing in my design, so shift, select all of those, right click, edit selection, and say no for enable. What that does is it will change. I hit the enter key, that will change them all to no. PS2, select that range, right click, edit selection, no. To turn those off. Here's the other switches I'm not using. So if I want to turn off everything I've used, since they're all grouped together, I could do that, and then I could go ahead and recompile. Yeah, I want to save the changes to the assignments. I could recompile, and then that warning about the unused pins will go away. There'll still be warnings about the IO connection. So I'm just showing you some different things that you can do to deal with various warnings you may or may not want to see. All right. And right, we still get some pins have incomplete IO assignments. Like I said, those are big. That has to do with some things that we're not implementing the board, some corrections that, like I said, even if we try to make the correction that I find on the Altera website, doesn't get rid of this warning. So we'll live with that. All right, let's go ahead and go to tools. Netlist viewers, RTL viewer is not ready yet because this is still running. So before you program the board, right, when you're satisfied that your compilation step has gone as expected, you can live with the warnings that are there, and you're ready to program the board, right? You actually have to have the board physically plugged into your computer, which I don't at this time, right? And we'll do that in class, and then I'll do a tutorial and post it at a future date when I have a board with me on how to program the board. I've actually provided students in my class a PDF of how to do that. It also tells you in the user manual as well. All right, so last thing, tools, Netlist viewers, RTL viewer. All right, so here's our hardware level, our top level. We can see switches 2 down to 0. So here this still looks familiar. Switches are being wired to the LEDs. Bus 2 to 0 on the LED R bus, right? We've still got that grounded signal here. We can see our outputs then are being wired over here. So if you want to drill down into there, once we drill down into there, right, within that hardware level, here's our instance of our top level module, right, with our A, B, and C connections. Again, you could drill down to see the other circuits we made. So the RTL viewer, if you, right, gives you a good snapshot of what your design looks like, right, symbolically. And then if you go all the way down to the lowest level circuits, which gates have been used to implement it. All right, that is the end then of this tutorial of using these hardware signals within some of your lab assignments, right, within an instantiation of a module. All right. So I made this for my student in digital logic design lab. Right. Hopefully it's helpful to anybody else that's working with an Altera board as well. All right, thanks for watching. Post any questions. Like, subscribe, all those YouTube things. All right, see you in the next tutorial and see my students in class.